right, can everyone hear me? Okay, great. So I'm going to talk about a new compiler that we developed for the NetKAT language. NetKAT is a programming language for programming networks. So I know this is difficult to believe, but networks have actually just very recently really become programmable for the first time. And so people have started creating high-level programming languages for networks that allow application developers to develop applications in a modular way without having to worry about all the low-level details that go into actually executing these applications on switches in the network. And so a compiler can then take these high-level specifications, translate them down to low-level rule tables, and these rule tables can be installed on modern networking switches. Many recent networking platforms rely on these high-level languages because they simplify application development tremendously. And they allow the developer to reason precisely and formally about the behavior of their networks. A great example for this is SDX, a paper from SIGCOMM last year, where they describe a software-defined internet exchange. An internet exchange point is a place in the internet where several different internet service providers come together to exchange traffic. So for example, if you want to download a large file and it happens to be hosted on a Google server, but you get your internet through Verizon, this is kind of the infrastructure that makes it possible for you to receive that file. So it's a very crucial infrastructure of the internet. And the system they describe here makes that infrastructure more flexible and ultimately more efficient using these kind of high-level concepts. But let me draw your attention to a figure in the evaluation section of the paper where they look at compilation time. And their system takes more than 10 minutes to compile these high-level policies that the internet service providers can describe in the system. And in fact, they only evaluate the system up to 300 participants, but the really large internet exchange points in the world all have more than 600 participants. So clearly, current compilers are too slow. They don't scale to the really large systems. And this is especially a problem because compilation is typically not a one-time thing, because networks are dynamic. And so as traffic patterns shift and links go up or go down or come up, you typically have to recompile your high-level policies. There's a second problem that maybe is even worse. Current compilers are limited to what we call local languages. So in these languages, you describe the behavior of the switches in the network, but you can't really describe the behavior of the network as a whole. So kind of describe global behavior such as forwarding paths. And so that's where our paper comes in. We describe the first complete compiler pipeline for the NetKAT language. And it comes in 3 parts. We have a local compiler, which you can think as a drop-in replacement for current compilers, only it's more than 2 orders of magnitude faster. Then we have a global compiler, which raises the level of abstraction and allows us, for the first time, to compile the full NetKAT language. And so in particular, it allows you to program the network as one global thing instead of describing the behavior of the particular switches in the network. And then finally, we raise the level of abstraction even higher with a virtual compiler that allows programmers to specify their policies in terms of virtual topologies. On a technical level, these 3 contributions are intimately related. The speed up of the local compiler is due to a new intermediate representation. And that same intermediate representation is the basic building block of the symbolic automata that the global compiler relies on. And then finally, the virtual compiler uses a global program to implement virtual programs on top of physical programs. And it synthesizes these global programs from a 2-player game that we will formalize later. So I've been talking about these compilers. Now let me specify explicitly what the source language and the target language is that we're talking about here. So the target language are so-called Match+Action tables, and they can be installed on modern networking switches. You can think of them sort of as ordered lookup tables. So whenever a packet enters the switch will look for the first row that matches the packet, and then apply the actions from that row to the packet. But the main takeaway here is that these tables were designed for efficient execution in hardware. So they have a little bit of a quirky semantics and some weird restrictions. So for example, you can only match on conjunction of positive tests. can't use negation, can't use disjunction. And in particular, they don't really allow you to develop applications modularly. So we really don't want to create these tables by hand. This is really tedious, and it's very easy to get wrong or hard to get right. So the goal will be to create one such table for each switch in the network. But like I said, we don't want to do that by hand. We want to create these tables automatically from a high-level specification in the source language. So let me show you kind of a nice compositional language to specify the behavior of networks. So this is the NetKAT programming languages that has been developed over the last few years. And you can think of it as consisting of several sub-languages. We have a Boolean algebra, which allows us to match on subsets of the packet space, so to build classifiers. We have a Kleene algebra, which gives us nice modular composition operators, and in particular allows us to describe forwarding paths using regular expressions. And then finally, we have some primitives to modify header fields and to send packets across a link from one switch to another using this link syntax on the bottom here. Let me really briefly talk about semantics. So if we ignore the links for a second, you can think of all these programs as defining functions that map an input packet to a set of output packets. So for example, if you wanted to drop all packets, you would just map the packet to the empty set. And so this fragment of the language we call the local fragment because it describes the behavior of individual switches. But if we add links back to the language, we get what we call global program. It describes the behavior of the entire network as a function. So in particular, it maps an input packet to the entire path that we want that packet to take through the network. So let's look at how to actually program in this language by an example. So here we have two switches connected to each other, and we want to forward packets along these two red arrows. To implement this as a local program, we have to specify the behavior of switch A and switch B. For switch A, this is simple. We just send all packets out through port 3. But now we have a problem, because switch B has no way of knowing whether an incoming packet is on the top path or the bottom path. So note how these paths overlap in the middle. So we actually have to modify the policy of switch A. Switch A has to kind of tag packets so that switch B can read off that information and act appropriately. So this is tedious and actually difficult to get right if you look at larger programs. To implement the same thing as a global program, we can describe the whole behavior as a single program and directly encode these forwarding paths. So we simply take the union of the top path and the bottom path. And these paths can be encoded using the link syntax that sends packets from switch A to switch B. Finally, we can simplify this even more by implementing the policy in terms of a virtual network. So first, we have to select a virtual network. A sensical choice here is a so-called big switch that exposes ports 1, 2, 5, and 6 from the underlying physical network on one single virtual switch. And then the policy becomes trivial. We simply send packets that arrive at port 1 out through port 5, and packets that arrive at port 2 out of port 6. So now let's actually get started and look at the local compiler. It takes as input a local program, so a program that defines the input-output behavior of switches. And it outputs a collection of flow tables, one for each switch. The main challenges here are to do this efficiently while keeping the size of the tables small. So there are already compilers who do this, and let's look at how they traditionally have done this. So for example, let's say we wanted to compile a union of a routing policy and a monitoring policy. So we would start out by translating these policies individually to tables, and then we would compute the union directly on tables. This basically amounts to taking the cross product of the rows in individual tables. And this turns out to be very inefficient. Just keep in mind that tables were designed as a hardware abstraction. So there's certainly not an efficient data structure for performing these kinds of operations. And so this gets quickly very expensive and creates large tables. So our solution is simple. We just introduce an intermediate representation and then perform these kind of operations on that intermediate representation. And once we have compiled the whole program to the intermediate representation, as a last step, we translate the intermediate representation efficiently to tables. So the intermediate representation that we came up with is called forwarding decision diagrams. And the name comes from the fact that we borrowed heavily from binary decision diagrams. But the main takeaway here is that once we have this nice intermediate representation, we can perform all the NetKAT operators, so union, sequential composition, cleany star, and negation, very efficiently on that intermediate representation, using all the standard tricks that you know from binary decision diagrams. So next, let's look at the global compiler. The global compiler takes a global NetKAT program, so a program that may contain links, and describes the behavior of an entire network. And the output will be an equivalent local program, so basically the behavior of the switches in the network. So to see why this is difficult, recall the example from earlier. In this example, switch A had to tag packets so that switch B could read of that tag and forward packets appropriately. Now, the local compiler will have to figure out when and where to add these tags automatically. This turns out to be very tricky to get right. And the problem is that whenever you have a union of topologies in NetKAT and they share a common path, the NetKAT semantics actually requires us to forward only a single packet along that common path. This is because the NetKAT semantic is based on sets. But if we add tags naively, that is, using one tag for each path, we actually end up sending multiple packets, in this case 2 packets, along that path. So that's unsound with respect to the semantics. The solution to both of these problems, interestingly, relies in interpreting them in terms of automata theory. So here's our solution. We start out by translating the global program to an equivalent NetKAT automata. In this automata, suddenly the state of the global program has become explicit, which is exactly what we wanted. Next, we determinize that automaton, and this turns out to be the crucial step to get rid of all these duplicate packet traces. Finally, we extract a local program from the automaton such that the local program emulates the execution of that automaton. So the local program uses tags to keep track of which state a packet is in. And then state transitions simply correspond to modifications of that tag field in the local program. Now, if we wanted to use fewer tags in our local program, we can actually do that as well. We simply minimize our automaton before extracting the local program. Now, these programs that these automata that I've been talking about here are not the normal automata that you know from regular expressions. So, for example, the transition relation is slightly more involved, and it contains the set of packets. One big problem here is that what you may call the alphabet size of these automaton is actually the square of the size of the packet space, so enormous. So we can't use traditional techniques to handle these kind of automaton. But luckily, it turns out we can represent the automaton symbolically using the very same data structure that I showed you in the previous section, namely forwarding decision diagrams. And so using that symbolic representation, we can perform all kinds of operations on these automaton. Even the power set construction to determinize automaton can be performed directly on these FDDs. To construct the automata, we have developed kind of a beautiful algorithm and borrow some ideas from Antimarov's partial derivatives and position automata from regular expressions. So if you're interested, please look at the paper. So let's raise the level of abstraction even higher and get to the last piece of our compiler pipeline, the virtual compiler. So the virtual compiler takes as input a program written against an abstract virtual topology. And the output we want to produce is a program that runs on the physical topology, but simulates the behavior of that virtual program. So the key to implementing virtualization is to think of packets as having two locations, one in the virtual network and one in the underlying physical network. When we start execution of the program, these two locations are consistent. They are in sync. But as the virtual program executes and moves packet across the network, consistency may be broken. And so it's our job to come up with a physical program that moves packets through the physical network in order to restore this consistency after each step of processing. Now, it turns out we can formalize this as a two-player game. There's this virtual player on the top that tries to break consistency, kind of the evil guy. And we have a player on the bottom, the physical player, that tries to restore consistency after each step. And kind of the punchline of this all is that we can synthesize this physical program P that we want simply as an encoding of a winning strategy in that game. So there's many more interesting things to be said about virtualization, so please look at the paper for the details if you're interested. So to conclude, let's look at some numbers. Here we compare our local compiler to the system that I showed you at the very beginning of my talk. So the dotted lines here on the top are the SDX systems, and the solid lines on the bottom are our compiler. And please note, this is a logarithmic time scale here. So you can see that we reduce compilation time from more than 600 seconds down to below 2 seconds. So this is more than 2 orders of magnitudes faster. We evaluated our compiler in detail. We looked at performance, scalability, the effect of several optimizations that we implemented, and the overhead of using global programming versus using local programming. And finally, we have a case study of the virtual compiler. So to conclude, I've shown you the first complete compiler pipeline for NetKAT that can handle the full language. It consists of a local compiler, a global compiler, and a virtual compiler. And it's fast, it's flexible, and it's fully implemented in OCaml. So if you're interested, go to GitHub and go check it out. Thank you very much.
Questions? Quick questions.
So in the process of mapping virtual to physical, the consistency issue that you deal with, this solves the problem of needing to speak to different OpenFlow controllers, or different OpenFlow switches, I mean, asynchronously. So there aren't any kinds of races in real-time timing when you update the network with the new virtual policy?
So the language we look at here, they describe static forwarding policies, right? So the idea is you install them and then you execute your network. We don't deal here with updates to the network. So there's separate papers on that and how to deal with that. But it's not part of this paper.
Got it. Thanks.
So at Popl 15, Damian Poos has presented a library for symbolic decision procedures for CAT.
That's right, yeah.
Are you using this library?
No. So the NetKAT language, so the automata theory for NetKAT is not the same as for clean algebra with tests. It's slightly more complicated. So yeah, we came up with our own implementation. And also, we're using this for a compiler, not for a decision procedure. So there's slightly different considerations to be made.
Okay.
There were too many good ideas in your talk. What is the one thing that you really like about this work?
So I think that the global compiler for me was the most interesting part. So we had many iterations of implementing this compiler, and at the very end it turned out, oh, it's all just automata theory. And so I think that's very slick and nice. From an application point of view, virtualization is an extremely powerful abstraction. And I could have talked the whole talk just about virtualization. And yeah.
One more very short question. So the compiler that outputs the local DFA, it sounded like you're running the same local program on all switches. Is that correct?
So the confusion is because, so it turns out we can write one local program that describes the behavior of all switches. We simply kind of guard against the switch we're on, and then compose that with the policy for that switch.
And then you have to prune that to get a small table for each switch?
That's right. So when we
deploy it?
generate the tables for the actual switches, we specialize the policy for that specific switch.
Thank you.
So no more time for questions, but please do take them offline. Let's thank the speaker.